But thank you for the grand entrance. We had a fantastic entrance with a lady that actually fell into the room, but she's okay. So we had a lady that fell earlier this evening. We were quite shocked, but she's okay. We're so happy that you're good and fine, ma'am. It's good to see that you're good. Right, the cafeteria will be open until 7 o'clock, just out the door to my right. At the toilets, if you need to go, out on the right is a door, open door, and when you turn left, you will find the men's and ladies. Ladies to the left and men to the right. My introduction tonight is black hole. That's the topic of this whole evening. Well, if you think of it, I think most of us actually saw a black hole plus minus around the 19th or the 20th of February, but we might have missed it, not knowing that you actually saw a black hole. Why? I opened my wallet and there was a huge black hole. All right. Now, black holes, all of us, I think, did do some study on black holes before you came. I did. I had to go to Google and research quickly a few things that I might not know. There's so much things about the stars and the universe that we don't know. So it's always interesting to go back and see what else you can read about, as our topic says, black holes. Light travels so fast. We all know that light travels 10 million kilometers in a year. It travels so fast that it travels around the Earth in about 7.5 seconds. It travels. No, I'm going to mix up my stuff. It doesn't matter. It's way faster than that. It travels around 7.5 times in 1 second around the Earth. There I have it now. Otherwise, it would have been very slow. All right. The nearest black hole, according to Google, Google is fantastic or scary. It might be correct or wrong. Says that the nearest black hole is about 2,600 light years away from us. And it also says that a black hole will not be able to swallow, it will be able to swallow the Earth in about 10 to 15 seconds. Well, that's what Google says. Anyway. Betelgeuse, we all know, is one of the stars in the Orion belt. And I always used to tell my grade 8s that Betelgeuse is about 724 light years away from us. So if I go out tonight and I look into the sky and okay, there's Betelgeuse. And then a few days later I go out again and I look and where's Betelgeuse? And I go check the next night and I don't see Betelgeuse. That actually means that star died 724 years ago because it takes so long for the light to reach us. And that's amazing. And that brings me to the best part, the Bible. Because Genesis 1 says that there was nothing. And what happened in Genesis 1? The Spirit of God was hovering over the face of the waters. And God said in verse 3, let there be light. And there was light. But if you read further, in verse 16, we only come to realize that on day 3, the sun and the stars were made. And I had to ponder about this for a few seconds and ask myself, if there was light in the beginning, why only was the sun and the stars created on day 3? And where did this light come from? And it struck me. Jesus. Jesus was the light and is the light of the world until the last day. And that's like amazing to think about. That when God said, let there be light, He put His Son in position, said, you will be the light. not only for creation, but forevermore. And that is beyond super awesome. All right, that's my opening. I would like to introduce to you the Dean of UNAM that is in charge of, actually this evening, and in charge of UNAM that put this whole thing together. If you haven't been into that planetarium, oh my goodness, don't miss it. It's amazing to see what technology can do. So please, if you have a chance afterwards, go sit down quickly and have a look at what they were able to put together, what technology has been able to do for us nowadays with that. That's really awesome. So without further ado, I would like to call up Professor Wiku Wahingu.
MC, thank you very much for this platform. It's very exciting this time of the day to see so many faces which came out to this very important event. My name is Wiku Wahingu, as it was mentioned. I am from the University of Namibia, and I'm the Associate Dean for the School of Science, under which this specific activity or activity that we have here is going to fall under. I'm here with some of my colleagues who have worked hard to make sure that this particular project has got a part to play in Namibia. And I'm also very optimistic that most of the faces that I'm seeing here today, we have got a good number of learners, because this specific activity is a very good motivation, particularly for learners who are yet to make their career choices. Myself, I'm not a physicist because this is coming from the physics side. I am a chemist by training, and the Department of Physics, Chemistry, and Material Science is one department, so we are all part of the same boat. So thank you very much for coming in numbers. I just want to give you a brief overview of the School of Science at the University of Namibia. We have got about 6 departments which are spread around the whole country. As most of you are aware that we've got satellite campuses. We have got 4 programs that are offered at the main campus here in Windhoek. That is the Department of Biochemistry, Microbiology, and Biotechnology. That is our first department at the main campus. And we also have the Department of Computing, Mathematics, and Statistical Science. That is one big department which is under the School of Science. The third department at the main campus is the Department of Environmental Science. That is where you have your GIS department, environmental biology. You also have forestry and the ranger management. They are all falling under environmental science department. And the fourth department is now the same department, physics, chemistry, and material science. The other 2 departments are in the satellite campuses. The Department of Geosciences is the southern campus. The Department of Wildlife and Tourism Studies is at Katima Mulilo campus. So those are the 6 departments that we have. First of all, let me thank the organizers. Let me not yeah, it's more especially the management of the school for allowing this particular event to take place here. And I would also like to thank Prof. Just 1 second, please. Yeah, Heino Falcke, yeah, for leading such a successful project to bring so much joy to our researchers and also to our young learners. This speech or this talk for tonight is going to inspire a lot of young learners. And some of them will be convinced at the end of the day today to say, I want to become an astronaut. And in addition to that, the department under Professor Bakes and Dr. Kasai, who are stayed there, are part of the department or the section of physics, they have been successful in this area, especially with regard to the HES telescope, the station that we have some 100 kilometers south of Windhoek. I wish, especially for young learners, if the school management, if you can hear me on this one, just it's a one-day trip, just go there and show the learners that site. It is so magnificent. You have these whole huge telescopes that are sitting in the desert there for some very good reasons. Please take a trip, plan with our colleagues here. They will take you there. I have been there maybe 4 or 5 times, but every time they are going, I'm looking forward to go to that place. So that is how good the place is. And of course, in relation also, or in collaboration with African millimeter telescopes. So there has been so many activities, project collaborations with regard to the African millimeter telescopes. So tonight, let us sit back, let us look forward to what the presenter is going to give us, and hopefully, like myself, I always get inspired when I listen to talks, especially for the first time. I always get out of something that is going to inspire me, so that, whenever these type of talks are going to take place somewhere, I will always be the first to go. So with these few remarks, and on behalf of the University of Namibia, we would like to welcome the presenter, wish everyone a very fruitful night, listening and all the excitement. I can see there is a very huge structure at the back there, which I've seen several times. I think you will have good times. And Chairperson, thank you very much for the opportunity. Thank you.
Thank you so much. Thank you, Professor, for your kind words. Yeah, we live in a country with vast skies, clear skies, and it's actually amazing to see what pictures we can take of the night. So let's get out and take some pictures of the sky. Big plans ahead, according to what I heard in the news and from sources about possible new telescopes, etc., etc. But to introduce our star of the night, I introduce Mark Klein-Volt, who is big behind the scenes with this whole project. Thank you so much.
Good evening. It is my honor to introduce the star of this show, and I'm really glad to see so many people here tonight. Some of them I already seen before on some of the many trips that I had here in the beautiful Namibia. Some of you may know him from Netflix, and I'm not kidding. It was actually mentioned just before dinner. We had dinner just before coming here. People were saying, we know him from Netflix. He's a famous movie star. But this man is actually one of the visionary scientists in the world. The man who first thought about making an image of a black hole. And he managed to do that. This man has received many prestigious prizes, not only in Europe, but also in the US. And for the work he has done, he has even received, or became a knight in the order of the Dutch Lion. I have to say it correctly. I always make a mistake. But he's a knight. I think he even came on his horse here tonight. Yes, and he has a sword, apparently. So be careful. So, ladies and gentlemen, without further ado, I will give you the star of the show, the visionary scientist, Professor Heino Falcke.
I'm glad to be here, but I'm now a bit embarrassed because there are probably no expectations for my talk now. So I hope I can fulfill all the wishes that, and the hopes you put into this talk. And I will try to take you into a journey to the end of space and time. I'm not going to just talk about black holes. I'll take you actually from the Earth all the way through our Milky Way to the stars and the galaxies out there. And we'll encounter the black hole in between. And I think that's the amazing thing, that if you start looking into space and actually go into space, what happens is your perspective changes. Your perspective of space and time changes. And I love that you started with Genesis. I had here a psalm word that many of you probably have seen. 1,000 years in your sight are like a day that has just gone by, or like a watch in the night, which reminds us that time is relative. It's sort of on the large scale in God's eyes, so to speak. What is 1,000 years? It's nothing. And I remember, you mentioned Genesis 1, creation of light. St. Augustine, famous church thinker, was thinking like, God couldn't, he couldn't take just an entire day. He can make light in a second, right? So time is relative. And in fact, that is very true. It's very true if you're sitting as a dentist and you're waiting, or someone is drilling in your teeth. Time feels very differently than when you are in a romantic dinner in the evening. So it's a very human experience. But physically, that's also true. Times run differently depending on how fast you run, or where you are on Earth, or whether you are in space or on the ground. In fact, if you go into space, time will run faster. You have a very accurate atomic clock, the best clocks you have, and it goes perfectly correct on the ground. You launch it into space, and then it will go 38 microseconds per day faster than here on ground. And you say, okay, what's 38 microseconds? Well, actually, if you use it to determine your location on the ground with a GPS system, you'd be off by 10 kilometers if you don't correct for that error. It makes a huge technological impact, those 38 microseconds. And that has all to do with the theory of general relativity that Albert Einstein developed in 1915, and that changed our view of space and time completely. In the years before, space was static and time was constant. It was eternal. Scientists were thinking that the universe was eternal. It was always there and would always continue. And what we learned since then is that actually the universe had a beginning, and that time actually is relative. And it comes from an interesting realization, and that has to do with the property of light again. I love that you started with the light, because light is actually the absolute in physics. With light, you measure space, and with light, you measure time. If you think about it for a second, what is space and what is time? Have you ever touched space? Have you ever tasted time? Space and time is always what you measure. You always need a rod or a clock to measure it. And the most fundamental clock, and the most fundamental ruler you can think of is actually light. Light is, how far is something. It's how long light takes to traverse. That tells you a distance. And light is a wave. It's like a clock. It ticks. And then, how fast it ticks actually gives you the time. And then there was one other realization about light, and it's that light always travels with the same speed wherever you are, how fast you are. This is something that was discovered in the, when we discovered the properties of light. And so light always goes with the same speed, 300,000 kilometers, 300,000 kilometers per second, 7.5 times around the Earth in a second. Always goes with the same speed. And what is speed? Speed is length divided by time. It's kilometers per hour. That's how you measure speed, or miles per hour, whatever. So the ratio between the two is constant for light, but length and time can actually change. Only the ratio between the two needs to be constant all the time. That's one of these very weird aspects of light that one realized. And then came gravity and Albert Einstein, and he was thinking about what gravity is, because gravity, which attracts you to the ground, feels also like acceleration. If you are in a lift, or in a rocket, you don't know, with a closed rocket, you don't know whether you're on the ground and it's gravity attracting you to the ground, or the rocket is accelerating and you are in free space. You cannot tell the difference. So gravity has also something to do with speed and motion. And then, Einstein was postulating that gravity, which attracts us, is actually a property of sort of space and time itself. And that gravity, like matter, actually curves space and time together. It influences space and time because it actually influences the way light behaves and light moves. And so if you have the Earth, it will actually, if you picture the space as a flat panel, which is a soft tissue or so, then every matter, you, the Earth, the sun, will make a little dent in that space. And if you have then light will go along this two-dimensional surface, which in real life is three-dimensional. But light will then go through this little dent. It will make a little curve. And that, in fact, we see. Light is deflected by gravity. In fact, each of you deflects light. If I shoot a laser beam at you, I may miss you because you slightly curve the light beam. Well, it's so little because all of you have, very, are not so heavy and massive, so you don't curve space-time so much. But if you were the Earth or a black hole, you would curve it a huge amount. And then you see, light is curved, but then if you go around a curve, you actually have to make larger steps in a way because the space is stretched. So you actually you stretch the wave. It has to make larger steps, and that means the clock ticks slower. As you stretch something, and so then you immediately measure time differently, whether you're close to the matter or far away. And that's what you see here, right? If you want to go around, you keep going around with the same speed, but the length becomes larger because the space is stretched. Time has to be longer as well. That's the other way. The ratio between length is longer, time has to be longer as well to keep the same speed. So that's the basic idea. And from that, everything else followed. If you've understood that, you've understood the theory of general relativity, and you can go home. Well, then, a year later, actually it was Karl Schwarzschild, actually in the trenches of World War I, he was developing, how light and space would look like if you would concentrate all the matter in just one point. You take the Earth and you concentrate, you squeeze it very strongly into one little point, and then how would space and time look around this? Of course, for them it was just theory. It was just mathematics. It was not reality. It was just a trick to make life simple for mathematicians. And what you would find then is that light would actually be bent and stretched so much that it would be swallowed forever. That it would actually be stuck because it had stretched to a lot of infinity, so to speak. And in fact, light would never come back at this point. And this point where light cannot come back, we call the event horizon. Why? Because light is the fastest there is in the universe. Nothing is faster than light. And so no information, no matter can travel faster than the speed of light. So if light cannot escape, nothing can escape. And that was a big shock, because it would mean that if these objects would exist, there would be something in our universe, in space, where light can go into, but you cannot measure what's inside. You could jump into it, you could see what's happening there, but you could not tell anybody. Because if you take a radio or laser or whatnot, or you'd shout, no information would get out. You'd eternally separated from the rest of the universe. And that's an embarrassment for physicists, because they want to measure everything. And now physics tells you, well, there is a fundamental limit where you cannot penetrate, at least in one direction. You can fall in but never get out. And Einstein was essentially scared by this, and he said, a fantastic solution, mathematics, but that does not exist in the real world. It cannot form. He had all kinds of ideas, and he published a paper showing in 1932 that these things that later became known as black holes could not form. Well, he was proven wrong. His theory we later proved right. And I tell you a little bit about sort of astronomy and what we've learned then. Because what we've learned is that the universe is not static, and that stars are not eternal, neither is the universe. Actually, stars undergo the same cycle of life that we undergo. If you look at the beautiful Milky Way that you can see so beautifully here in Namibia, we can't see it, we actually hardly can see it anymore in the Netherlands. But here in beautiful, you see all these dark patches. You've seen them, the dark patches in the Milky Way. These are dust clouds. This is like smoke, little dust smoke that is sort of pervading the entire Milky Way. And that's what you see here, a cloud of dust, smoke-like dust. And it's glowing red, because out of this cloud, young stars have formed. And that's something I will show you here in the simulation, what we can do in a computer, in the group here in Caltech. You see this cloud in the universe, and there is no wind that blows it away. It's just gravity is acting. And where there's a lot of dust, the dust starts to contract and contract further. And the dust condenses into little knots, and the knots become stronger and stronger and more dust, and actually they all turn into stars. Stars are born that way out of dust. Dust you are, and to dust you become, so to speak. And what you see here is over the course of 10 million years, how stars would form out of a dust cloud. So stars are being born, and you see here this beautiful, fireworks of young stars that are being formed in a dust cloud. And then if you zoom in, you would see something like this. This is a young star surrounded by dust rings. Looks like Saturn. I don't know if you've ever seen a picture of Saturn. And these are rings, but this is the size of an entire solar system. That's how also our star, our sun, was formed. The dust was contracting and forming the sun and the stars, and the rest of the dust was rotating around the sun, and then it formed also little planets. And sort of out of this ocean of dust, suddenly, solid matter like Earth emerged, and you would see these rings. And that's why all the planets actually orbit along one particular line, because they're all in one ring. And that's what we see here. And these pictures are just a few years old. Now we can really look at the universe with eyes of angels, so to speak, seeing pictures that no generation before us was able to see. We're really seeing a completely new world. And these pictures were actually made not with an optical telescope, but with radio telescopes. This is a collection of radio telescopes in Chile, which is the same latitude as here. They have the same nice view of the night sky, and that's where a lot of the telescopes are. And this is sort of one of these telescopes that makes and looks at these dust clouds. And that tells us, how stars are being formed. But then stars also die. What you see here is what we call a planetary nebula. And stars don't die quietly. They also die in fireworks. So you see at the end of the lifetime of a star, they'll shed their outer layers. They blow up, they become big, And then they blow out all the matter inside them. And that's very important also for life and the Earth. Because in the stars, nuclear fusion takes place. And hydrogen and helium, some of the basic elements of the universe, are fused into nitrogen, carbon, and oxygen. And so these stars, actually, they make new elements. And then they give it back to the rest of the universe. And if you zoom in again into this one picture, then you see these little things here. Each of them is actually the size of our solar system, actually twice of them. And then the tail is sort of 10 times sometimes the size of our solar system. And they contain new dust, enriched with new molecules and new elements. And this is essentially dust, star dust. And out of those new stars and new planets form. And so what you read in Genesis, for dust you are and to dust you will return, is very true, even on a much larger cycle than you ever might imagine. You are stardust, and you become stardust again in the long future. And then if a star is very big, the giant stars, which only live very briefly, they actually explode in a giant supernova explosion. And that's what you see here. That's the leftover of a very big star. And what you see is this shell of outside the star, and then you have this giant explosion. And these run with 30,000 kilometers per second into the universe, these shock waves. And in the center, the central part of the star will be compressed. So we have a huge pressure. And so all the matter will be compressed into an object that's just a few kilometers in size. An entire sun is compressed into something that's just a few kilometers in size. And then you have so much gravity, because you have so much matter in such a small space, that it keeps contracting. Because it's like something collapsing, and it keeps collapsing forever. Because the smaller it is, the more matter you have in smaller space, and becomes smaller and smaller, and that never stops. And it eventually collapses into just one little point. And that's how a black hole can form. And that's what we learned from looking at the life cycle of stars, that black holes have a possibility to be made in the universe. And they are part of this big cycle of life in the universe. Now then, you look further. And in fact, that is the Andromeda galaxy. That is the farthest object you can still barely see with your naked eye. It will never look as beautiful as this one. If you're in a very good location, you can see that something very, something a little like a nebula there, if you're lucky. But you have there is 2.5 million light years away. So you're always looking 2.5 million years into the past. And you see 200 billion stars going around the center. And that's exactly how our own Milky Way would look like if we were able to go out of the plane of the galaxy and see ourselves. We'd have to travel 1,000 years with the speed of light to actually see ourselves like this, or even 10,000s of years. So we look at our neighbor to understand how we look like. And so you have this giant disk of stars going around the very center. And there are, we estimate, about 100 million little black holes in such a galaxy, all around the entire galaxy. And 200 billion stars, of which, in this case, we are one. If you look at, I think the Afrikaanse Privaatsschool is somewhere here in the Milky Way. And it would take from here to the center of our Milky Way 27,000 years to travel with the speed of light. It's 27,000 light years across. These are the dimensions we are talking about. And what's important, in the very center, well, we have one star here. We have millions of stars in the center of the Milky Way. And then you have many little black holes, and they come together, and they actually swallow each other. And then, one black hole becomes bigger than the others, and it swallows all the others, and it starts growing. And in the end, you have not a little black hole, but you have one giant black hole in the very center of the Milky Way. And we think every galaxy has a very supermassive black hole in the very center, which is the super monster of all black holes in the universe. And that is the basic picture we had. And then if you look at our Milky Way, this here is a picture of the Milky Way and the optical, and you see all these dust clouds here that you cannot see so you cannot see through with your eyes. But then if you zoom in and you switch to wavelengths where light can penetrate the dust, you go to near-infrared or radio light, then we can actually see into the very heart of our Milky Way, which you cannot see with your eyes. And if you go to the very, very center, then you see actually a couple of stars in the very center, 27,000 light years away. And what you see here is a movie over 16 years. And you see that these stars are actually moving. And some of them move with 8,000 kilometers per second. And you see this star here, this star, oops, no, the wrong direction. No, shoot. Here, this is, this star goes on a perfectly elliptical orbit with 8,000 kilometers per second thereabout. And so if you go around a curve with 8,000 kilometers per second with your car, you get trouble with the police, I guess. Secondly, you need very good tires or someone who keeps you, fixed, that you don't fly out, right? And what force can be so strong to keep a star with this speed and go around a point? Well, the answer is you need a lot of matter. You need 4 million stars concentrated in one point to have so much gravitational attraction that these stars can stay bound and orbit around this point like the planets orbit around the sun. And that means what we need here is, in this point, we need about 4 million suns concentrated in that region. And there's nothing to be seen. There used to be nothing to be seen. And so people said, this is where the black hole in the center of our Milky Way is. And that's where, I started my investigations. Now, this is the same region again with a radio telescope. In fact, that is made in South Africa with the Meerkat array, where there's a big array of radio telescope. And this is the most beautiful image ever made in the radio of the center of our Milky Way. And it glows because radio emission goes through the dust. Because in the radio, you have cell phone reception here inside. Radio emission can go through windows. And it can go through the dust, you can see it. And you see here, this is the central region, and then here, this is the region where the center of the Milky Way is, and if you zoom further in, then there is this bright point. There's a bright radio source here, which is emitting radio light. And people said, no, maybe that is where the black hole is. That's where it should be. And I was working on it as a PhD student. I was wondering, could we ever see that? Can we see if it's really a black hole? What would we be able to see, and how can you see a black hole? Well, how does a black hole look like? Well, you can see. It's a black hole on a black background. It's not much to see. So what you need to do, you need to shine light at the darkness to actually expose the darkness. Because what do black holes do? They absorb the light. And so there will be light missing if you shine light at a dark hole. And so that's what we show here. So you have, this is sort of supposed to mean where the black hole is. And then we shoot laser light at this black hole. So I take this here, I shoot it in this direction. I know the light will go straight. I shoot it at a black hole. And what you see here, the light will go in this direction, and then will be bent by the force of gravity, as I described before. If you go even closer, it will be bent. It will actually go around the black hole. In fact, there's a point where light can go around in a circle if you shoot it at a black hole. So if I would stand here near a black hole, I would look in this direction. My vision would look around the black hole, and I would see the back of my head in front of me. That's how it would look like. Of course, you wouldn't be able to stand there. The pleasure would be short because you would fall into the black hole very quickly. But, if you ever fall to a black hole, look into this direction, enjoy that for a brief moment. It's and so that's what happens. And so all this light that comes a bit too close will be absorbed and will not be seen. So what you will see in the end is actually a dark region in the very center. And these days we simulate how black holes work in supercomputers. This is a supercomputer simulation. You see matter go around a black hole. It's bright. It's actually the brightest emission you can have in the universe, hundreds of billions of degrees, because the matter goes around with, again, almost the speed of light. It's the brightest temperatures. It radiates enormously, but in the very center is the darkest darkness you can imagine, because that's where all the light disappears. So the center is not bright, but the center is dark. And so if you calculate this, then you would, you choose the right frequency, the right light to look at, you would expect to see something like a dark region in the center and then the light going around in a circle. And we can tune a little bit what part of this, this matter we look at, depending on which frequency we look at. So if you choose the right frequency, then you should be able to see that. This is something that we predicted. In fact, I predicted this 20 years ago, and this was then the latest one in 2016. And if you look at this, how big is this? If you look at the biggest black holes in the universe, the center of our Milky Way and then some other galaxies, this would be as big as a mustard seed in New York as seen from the Netherlands. Okay, now I have to calculate what that would mean from Namibia to somewhere else, probably from here to Chile or so. You put a mustard seed somewhere in Chile, and then you want to see this. And so you need a giant telescope to actually be able to resolve something that small in the universe. In fact, if you want to do this in the radio, you need a telescope the size of the entire world. And well, so then you build the telescope the size of the world. And the way you can do this is by combining telescopes around the world into a virtual network. And I'll actually skip some parts here because I'm already too slow and skip that part. And so that's what we did in 2017 for the first time at these frequencies. We combined radio telescopes around the world. Well, world was very limited because it was only the Americas and Europe. And we'll come to that later. In Mexico, Hawaii, South Pole, Chile, Arizona, and Spain. Sorry, this was a German slide. And we are combining these telescopes. The light, the radio light, was stored locally on hard drives. It was time-tagged with atomic clocks. So we knew exactly when the light would arrive at each radio telescope. And later in a computer, we could combine all of this together to make an image. And that process is actually pretty much doing what a real telescope would do, just with electronic means. And that was a big adventure. I mean, these telescopes are in very remote sites because we look at high-frequency radio emission, which doesn't like humidity. So you want a dry and high site to have these telescopes. And so there's South Pole is very dry. It's also very cold. There's Hawaii. It's very high. It's 4,000 meters high. Mexico. There's Chile here, as I said. Arizona, also very dry. And I was in Spain at this telescope, because it had the best food, actually. They have Andalusian food, and they really take care of you. In Arizona, you have to bring deep-fried pizza, which is, after 10 days, you're getting tired of it. So anyway, and so we had our big group, international group from our team in Radboud. We actually had people everywhere except South Pole. Problem with South Pole is you have to stay a full night, but a night takes 6 months, as you know. So it's you go there, and then 6 months with darkness, and it's not a real pleasure. And this year the crew in Chile with one of us. This was a crew after the observations. It's very tiring because we were observing day and night, really. So, and then we got together with this big group of scientists around the world to actually reduce and analyze the data. And that was a long process, and I'm not talking about this. If you want to learn more about this, there are going to be other talks. But at the end of the day, we were convinced what we saw was right. We split up in different teams. We did everything at least twice or 3 or 4 times, people checking each other, because you can do this experiment only once. You only have one Earth to make this experiment. And in fact, when I saw the first results, I knew this is going to be interesting, because it's looking exactly like I was expecting it. And that's very dangerous in science. If it's the first time you switch on an experiment, it gives exactly what you want. You should be very careful. Because you could be easily fooled, by your own emotions. Because you shouldn't try to get what you want. You need to get what nature tells you. Yeah, that's very important. So I was very nervous about myself and everything else. That's why we split up in different groups, and it was very, very tough. People checking each other and so forth, and criticizing each other internally. Oh, you're doing this wrong. You're doing this wrong. I have a better method, and so forth. But in the end, we were able to agree. And then the big day arrived, April 10, 2019. We're preparing for the big press conference. This was the one in Brussels in the EU headquarters. We were preparing for this. And this was sort of the first press conference ever in the headquarters of the European Commission. And it's actually the most successful press conference ever. I later learned that the tweet, for example, from this press conference I had was the most successful tweet of the European Commission ever in their entire history. And then, I was allowed to present this result for the collaboration, and that's the movie I showed. And this is, starting in Chile, and we're going to see a zoom of a factor of 1 billion. Factor of 1 billion zoom factor that we have in astronomy by combining different telescopes here. And we're looking now not towards the center of Milky Way, but towards another galaxy, which is 55 million light years away. We're looking 55 million years into the past. And what we're seeing here is a big bubble of radio emission, 240,000 light years across. And all of this is coming from a plasma beam shooting from the very center of this galaxy that we can follow and get closer and closer. And we see this plasma shooting out with almost the speed of light. And then we saw our image, which looked like that. And that was exactly what you had expected. You see this ring of light, and you see this darkness, the shadow, where the light disappears. You're really looking at the end of our knowledge, the end of space and time, and it's right in front of your eyes. Some people say it just looks like a donut. You see this often in an ugly donut. But it's, for physicists, it's the most beautiful donut ever, because that's how far you can go with your mind and your telescopes and your knowledge. And what happens inside a black hole, we don't know. We may never be able to find out. So that's what makes it so special. And then, this made headline news, actually really around newspapers around the world. There were 4.5 billion people saw that image because it was on almost every news you could think of. The internet was really crazy about it. There was cats and black holes and all kinds of things were showed there. Trump with a black hole. And people were going crazy with this. And it became an iconic image. There was a company who would try to claim that image. And they got a big, it's called shitstorm on the internet above them. And they lost 200 million euros in one day by trying to claim that image. So that's, I like to think of this as the money value of this image, 200 million, the cost. And then in May last year, and I think we had a press conference here in Windhoek as well, we were able to show that image, zooming finally into the center of our Milky Way. And now switching to radio light, see all the radio emission from our Milky Way, not what you can see with your own eyes. Now seeing the one from the South African, the Meerkat image, zooming further in. These are magnetic field lines. This is a big supernova explosion from 40,000 years ago. Streamers of gas going around the center. And then this ominous, this weird dot here in the very center. And finally, with the Event Horizon Telescope, with our big experiment, we were able to see this. Not a very pretty donut, but roundish thing, again with a shadow. And the most important thing, it was exactly the size as predicted. Within 20%, the size of that ring was what we expected to see. And that is, if for an astronomer, usually we are happy if something was in a factor 10 correct, right? But within the error bars to really measure this was an amazing moment. And so if you go back, this is a prediction that we made in 2000. This is the galaxy M87. This is our Milky Way, and you see they all look very, very similar. And that's a beauty sometimes of physics, that you can make predictions and you can see them. And so first it's just fantasy. It's the theory, and then you see it sort of with your own eyes. And that moment is such an awesome experience in science to be able to see that. First you believe in it, and then you see. And it's also important to realize this is a very different. This is a galaxy which is 1,000 times bigger than our own Milky Way, and also the black hole is much bigger. So if you look, our solar system would be that size on that image. And on that image, this is Mercury's orbit. That would actually fit inside Mercury's orbit. So very, very different sizes. And the matter will go around this black hole, this in 12 days, because it goes with the speed of light. And in the center of Milky Way, it will go around in 12 minutes. So all that stuff will go around. So one of the future goals we now have is not to just make an image, but to make a movie of a black hole. And that is one of the reasons that why we want to come to Namibia. That was the thought. We were here in 2015. Before we made the first image, we're talking with people and we're looking at the Gamsberg, which is the second highest mountain in Namibia. And the nice thing is Namibia is very close to South America. And it has the center of the Milky Way right above you. And you're a dry country. Well, you may not see this as an advantage, but for an astronomer, it actually is gold. And so I always say, you have an unfair advantage compared to like the Netherlands, which is flat and wet, right? And so the idea was to place a radio telescope somewhere in the center of that mountain. And this is a view from the top. It's actually a spectacular view up there. And then what you see here are the connections that Namibia would make. It would connect to the South Pole, to France, to Spain. It would connect to Chile. It would also connect to Arizona. It could even connect here, this is California, and Mexico, it's Mexico and Chile, and that would even be very briefly connecting to Hawaii. And all these connections deliver new information. In fact, if you make an image, and you make a simulation, and you take the first part of the experiment, where we don't have enough telescopes, it's just Europe and South Pole essentially, we cannot make an image. And so it would look like this. Adding just one more telescope in the first hours, we suddenly could see the ring. And then we could make a movie as well, seeing how it changes from 15 minutes to another 15 minutes. And that's what you see here. This is a model simulation. You see sort of something going around the black hole. And you have here this European side of the array together with the Africa millimeter telescope, and you should be able to see a bright blob going around. And that would deliver us much extra information and sort of in yet another step in the exploration of black holes and how they work. Now I want to come to the end, but zoom further out. This is now a view into the universe with a big galaxy in the very center. Do you want to guess how far this is away? I see three kids are almost falling asleep. Do you have an idea how far away we are looking now? Any idea? So the other galaxy was 55 million light years away. Anyone else wants to guess? 14 billion. Well, that is a too high side. This is only 2 billion. So the universe is almost 14 billion years old. That's true. But this is only 2 billion light years away. So you're looking 2 billion years into the past. And everything you see here around is another galaxy. Then each of these galaxies has another 200 billion stars. So in fact, if you count up all the stars in the universe, you have as many stars in the universe as you have grains of sand on the beaches of the world. So that's how many stars, how big that universe is. And if you then switch on your radio eyes in the very center, you actually see that something's shooting out from that particular galaxy. Again, it's a supermassive black hole. This is our simulation again, at the very heart, which actually is powering this powerful galaxy. Each of these galaxies has these 200 billion stars. It has these supermassive black holes. And in fact, if we look at the evolution of the entire universe, these black holes influence and change and shape the way the universe evolves. So black holes are also not only death, the signs of death, they also help to shape our universe and help to create. And so they are an integral part of our universe. So I want to end you again with a biblical quote, coming back full circles. Lift up your eyes and look to the heavens. Who created all these? And I think that is something you can do so wonderfully here in Namibia, seeing it at the Milky Way and the stars. Look up. And I think, and realize how beautiful, how big this creation is. And don't forget that we are very special stardust, because we can think about that universe. We can hope, we can love, we can believe. That's what all these stars cannot do. We are not powerful, and we cannot, if you take away the Earth tomorrow, the rest of the universe will not care. But it's the stardust that you are, your love, your faith, your stories, that will be lost. And that's what makes us special. It's not our power, it's our curiosity and our faith and our love that makes us possible. That makes us important, I think. And that's something that technology also tells us, if you think it a little bit through. Technology gives us a new view, but it also shows us that there's a limit to our knowledge and to our power. And that's what I want to leave you with. Thank you. I'm afraid I spoke too much again, but it happens to me once in a while. So.
But we have time for questions. No, we have time for questions that Heino can answer.
Yeah.
Maybe a few. Who wants to go first?
I'll probably go down here, and I'll grab your and let you speak into the microphone. If you can make it short, that'd be great.
Professor, I would have the question. For example, did you deliberately look at a galaxy, showing us the galaxy like that, or would you see the same black hole on edge on if you look into a galaxy edge on?
Yes. Now we chose those two galaxies because they have the biggest black holes that are closest to us. These are the center of our own Milky Way is of course the closest spiral galaxy, and this M87 is the biggest of the giant galaxies in our local universe. And so that's why we chose those. And this black hole is it's round. And that light goes not just in a ring, it goes in a shell. Everywhere is this. So from wherever you look, you would see such a ring. Sometimes you would see it a bit more pronounced on one side because of rotation and beaming effects, but in principle it's a shell and not a ring. That's important. It's not a donut. So there were other questions. So here, this guy is in the back, and then I'll come to you.
Thank you, Professor. Sorry, my question is more in regards to your joke. You said it would be a brief moment, but if you said that time is relative, wouldn't it maybe extend and stretch out at that point? You said the joke, there would be a moment where you would see the back of your head, right? So my question is, would it be a long moment or a short moment? Would time stretch out? Yeah. Would the time stretch out, or would it?
I think it's actually a much deeper question than you may realize, because time is relative depending on who looks at it. So if you fall into a black hole, it will be a short moment, unfortunately. If your family looks at you suffering, it will be a very long moment, but also physically, because they will see your time being slower and slower as you get closer to the black hole. That, I think, is actually the way it works.
Thanks, Prof. When you were giving your talk, you mentioned how the formation of a black hole starts with a star, a very large star that exploded, and it sort of implosion. That implosion causes a center of mass. What happens after that? Is this like a life cycle of a star?
Yeah. No, actually, when the star explodes, the dust and the outer shells, they will continue in this life cycle of stars, and they will form new stars and new planets. But the black hole will stay, and there's a big question of today's physics. Will it stay forever? Or will it evaporate eventually due to quantum effects? And we also have a new paper coming out in a few weeks, and so we think that actually not only black holes, but everything actually will eventually decay, which, if you look at I think we're living between Genesis and Apocalypse, but we should, make the best out of it. There's an end to everything, and there probably is an end even to black holes in the universe. So there are questions here. I'll come to the lady here first, and then try to make my way back.
No, thanks very much, Prof, for your very insightful talk. You showed the observation of a black hole at radio frequency, and that's UVF. Were you able to observe it at any other frequency, let's say UV?
Yes, it would look similar in other frequencies like X-ray or optical. That is indeed true. But we have no telescope that is so sharp to see that has such resolution. So because that virtual radio telescope, worldwide telescope, is a factor 1,000 has higher resolution than, for example, the Hubble Space Telescope or the James Webb Space Telescope. So I'd love to see it in other wavelengths, but you'd have to spend much, much more money to build that and have sort of lots of ingenious ideas to build such a telescope. So there was the question behind there.
Prof, thanks for your talk. It was wonderful. I'm sure you're aware there was two papers published very recently on black holes being a repository for dark energy. Would you like to comment?
Yeah, I saw that, and I talked to some of the experts, and the experts still scratching their heads what that actually means. My gut feeling is this is vastly over-interpreting their results. But you never know. It's an interesting idea. I wouldn't change my view of the universe right now. But who knows? You have to keep an open mind. But yeah, there are many things that don't really make sense. But yeah. There was a question here. Oh yes, okay. So is it you that had the question? No, okay.
Yes, thank you very much, Prof. This is certainly very enlightening. You have mentioned, of course, that the black hole, when the light goes into a black hole, there's a point that it doesn't come out, and therefore we don't know what is after that. But certainly as scientists, I'm sure you have theories. What do you think happens? What is in there?
We can actually calculate what it would be falling into a black hole. You can calculate because the mathematics would continue, so you would just keep falling towards a black hole. You may not even see that you are inside the black hole. That's also an interesting aspect. If you fall into a supermassive black hole, you still think the black hole is in front of you, but in reality you're already inside. That's one of these illusions. But at some point you would just compressed into one point, and then you cannot think anymore, you cannot feel anymore, you cannot measure anymore. And we don't even know what it means what time means in the singularity in the very center, what space means, because space is infinitely extended in one direction. So our concept of space and time stops at that singularity. And we think that there may be quantum effects, quantum gravity effects that may play a role there, but we have no theory of that. And so if you had that theory, and it were correct and could be tested, you have not only one, but maybe 10 Nobel Prizes. I don't know. Because this is one of the big fundamental questions of modern physics. That's maybe another movie. Now it's actually something we cannot measure. Okay, maybe one or two more questions. I see there are many more, but we probably...
I would say it's not a hole, it is a tube.
Yeah.
And the tube, the length of the tube depends on how big the Milky Way is.
I think if you think two-dimensionally, you better think of a tube, but that tube is actually infinitely long and deep. But its mouth, so to speak, is larger the more mass is in there. So I think it's a good way to think about it. So 2 more questions perhaps, and then...
Thanks. You mentioned you did your PhD, and it must be some years ago now. What's the most...
Yeah, I could tell.
Yeah. And you showed modeling and use of computers, etc., and huge telescopes. What's been the most exciting thing you've observed? Huge changes in astronomy and your own research. What's been the most exciting developments, apart from your concern with black holes? What else in the astronomy field?
I mean, there have been so many things. I mean, when I started, we didn't know about the size of the universe. And now we measure it with extreme precision, how large the universe is. We found the first planets. We not only one planet, we have thousands of planets that we found. We may find, maybe habitable planets at some point. And yes, seeing a black hole for the first time was certainly a highlight. I mean, I know many of my colleagues who was watching this press conference said they shed tears when they saw it, because it was such a. And now it's common. It's just you talk about this and it's normal. But before it was sort of unthinkable, and maybe more things will happen. And then
All the galaxies look like a disk. And I even heard that the universe is kind of a disk. Is that true?
No, the universe seems to be fairly isotropic on large scales. This has to do with the angular momentum being conserved, and so while everything rotates, it actually will like to go into a disk which has the largest angular momentum. Yeah. Okay, I think we'll have to stop here. Do you want to say a few more words, or?
Yes. Okay, thank you very much. Thanks for the interesting question. There will be time after this movie to bother Professor Heino Falcke. I'm sure he will be delighted to answer your questions. I would like to give him one more round of applause, please. He's not done.
Thank you. I didn't make any commercial for my book. I have a book, Light in the Darkness, Licht im Dunkeln. It's actually in 10 different languages, so if you want to read upon this, just Google it. And I just want to say a few words about the film that's coming up. Is that okay? Because we have this mobile planetarium. The idea is in the Netherlands. We have this mobile planetarium program which goes to all the schools with volunteers. And we have a team here of volunteers from UNAM, and there's Amanda standing here, and there's Lot Franz from UNAM, and Maaike Pierik is here, who've been organizing this team which goes to some schools to show this planetarium program. When we came here the first time in 2015, 2016, we were thinking about, wouldn't it be good, can we do this? Would that work in Namibia as well? And then Mark and this team tried this out and worked fantastic, so now we have the mobile planetarium here. At the same time, we thought, we should show something. What is a program we could show? And then we talked with a filmmaker in the Netherlands who makes the best planetarium movies, the highest quality, and even tells stories, which usually is not told in a planetarium. And so we said, let's make a film. And that film will be actually shown in the top planetaria around the world. It's a commercial film. And today we actually get a flat screen version. It's the first time it will be shown to an audience of that size. And in the flat screen version, you don't have to stay. If you want to go home, you can go. It's actually a 25-minute film, but I think it's quite inspiring. It shows telescopes, it shows the people, and it has a nice little story. And actually Namibia features quite well in it, because we wanted to use it a little bit also to showcase the Africa Millimeter telescope which we squeezed in. So you'll see some scenes. Unfortunately, it was shot during Corona, so and so you'll see sometimes there's a scene like in the university where just you don't see any students. Well, it was at the height of Corona that we had to do this, and the film was started. There's a main character. There's a female astronomer who is played by an actress, and she delivered 2 children during the production of this movie, just to give you an idea of what effort it took. And the guy, he went with an 8K camera, 360 degrees. This actually is 360 degrees. So if you would be at a planetarium and see this, you would see all around you the sky and the telescopes and everything. So this is a small screen. This doesn't do any service to the film at all. But it took really care to film all of these telescopes and so forth. So I can just recommend you to stay and watch this. I think it's entertaining and light. So it's a bit lighter than my talk.
So you see, it's always quite difficult to get Heino to talk and also to stop talking. So, so I'll give the floor now to the CEO of the Namibian Science Society. Ruth, here you go.
Thank you, Professor Heino, for already making half of my speech. Oh, sorry. All of a sudden, I feel microscopically tiny. Thank you very much for this amazing story that you shared here with us tonight. The sky clearly is not the limit and cannot help but feel excited and somewhat overwhelmed. Do we not live in an amazing age? An age where technology and knowledge have advanced so far that we literally can see into the center of our Milky Way. What excites me even more is that our Namibia, is one of the prime areas worldwide when it comes to astronomy. What most of us simply enjoy when gazing into the night sky is turning into an endless treasure for Namibia and its people. The Event Horizon Telescope collaboration has visibly demonstrated what can be achieved when people from all over the world work together. And I feel honored to have met some of these people here tonight. In a tiny way, we have managed something great here as well. By collaborating with AMT, UNAM, Radboud University, Hit Radio Namibia, and the Windhoek Afrikaanse Privaat School, we were able to make this evening possible. Thank you, Windhoek Afrikaanse Privaat School, for so generously providing the hall here tonight. Thank you, Hit Radio Namibia, for ensuring that the information was spread to dozens of media platforms. And thank you AMT Project, UNAM and Radboud University for allowing us to steal Professor Falcke for this evening. The Namibia Scientific Society is a non-profit organization which was founded in 1925. While originally the work of the society was to assist scientists directly with their research needs, the duty has now shifted to provide a platform for scientists and specialists. Presentations and excursions are regularly offered, and so fact-based information is shared with the public of Namibia. I'm delighted to say that the Society, even after the corona pandemic and in uncertain economic times, has over 800 members and is strong as ever. It is because of the generosity and the enthusiasm of its employees and members that the Society can offer events like these. It is also because of donations received by various institutions that we are able to record this event and later have it on our YouTube channel for those people that could not be here tonight. Thank you for all the support that we have received, and be assured that no donation or effort goes unnoticed. We, however, cannot do it entirely without funds. Every cent enables us to do more, and I ask you to open your heart, actually I'm asking you to open your wallet, when leaving the hall tonight. Tonight's funds will be shared with the AMT Planetarium project to assist with covering the traveling costs for this great plan, which now Heino stole from me. In case you have missed it on your way in, Namibia's own inflatable planetarium is standing at the back there. This ingenious device allows groups of up to 30 people to travel through the universe. The state-of-the-art software lets the pilot take you to all kinds of planets and galaxies, or even ices. What makes this planetarium so extraordinary is that it can travel all over Namibia, thus giving so many more people the opportunity to see deep into space. To inspire Namibians' future generation of astronomers, the first astrophysics masters and PhD students of UNAM have begun presenting a variety of shows in this planetarium. I have been very fortunate to see one of these presentations, and believe me, you do want to see this. We would like to round off this evening by presenting the film, which is titled Black Hole First Picture, and Mark, you're supposed to be praying play. This film has originally been produced to be screened in the planetarium itself and was adjusted to work on our flat screen here tonight. The film is only about 25 minutes long and sheds some light on how intricate the project of obtaining the first image of a black hole actually was. Thank you very much, and now I'll quickly help with the technology.